We're missing a few people. Oh, I don't have my screen on. All right, let's get started. And so we just need to finish up Le Chatelier's principle, and then we can do some other practice problems. And so Le Chatelier's principle, so let's again just put the reaction that we want to think about. And so you'll play with it next week, but it's our iron 3 compound plus our thiocyanate to make our blood red iron thiocyanate compound. So this is yellow, this is red, which kind of helps us. And so let's look into Le Chatelier's principle. And so basically we're saying we have this system at equilibrium. And right, if it's in equilibrium, it can go back and forth, kind of depending on how the system is disturbed. And so blah, blah, blah. And so some things to kind of note, but for our classes, the purpose of our class, we won't go too deep into the math. And so basically, right, no matter what, we could change the conditions, but then our equilibrium is restored. So this means that our K is always the same. And so we might have new concentrations, but again, right, same equilibrium. And then what we want to be able to do is kind of predict, well, which way is a reaction going to go depending on what we do to the reactants and products. And so let's kind of go through this. And so it says, okay, well, what happens if we add reactants? And let's look at this other graph too. And so let's look at this picture. It kind of goes along with the words that we're talking about. And we're saying, okay, well, let's add products or add reactants. And so we have reactants on our left side, products on the right. And then so we've opened up the system. So here's kind of, right, the key points so you can orient yourselves. So we're at equilibrium, and so this doesn't mean that there's no reaction occurring, right? There's still a reaction. These could be going back and forth, but the overall concentration isn't changing. And then now we've opened up the system. So we're basically opening or stressing the system. So we're doing something, right? So we have our happy system, and now we're manipulating it. And so we added in more of our product, so we can see the spiking here. And so now it has to reestablish equilibrium. And so all we're saying is, okay, well, initially, after we added this N2O4, that's going to drive the production of more of our NO2 here. And so we see that, right? So of course we have our artificial spike from adding in our N2O4, but now that we have too much of our starting material, that shifts it to the right. And again, so now we see that, so now it's making more product, and then product, so now we reestablish equilibrium. Of course, our N2O4 is consumed, and so now, right, we have a higher amount than we started with, but less than what we spiked with, since some of that was converted to our NO2. And so let's keep thinking about that. We'll go back to the text here. And so now it's saying, okay, as long as it's a reactant included in the equilibrium expression. And so what this is saying here, so it makes a weird statement that says, as long as it's not a solid or liquid. And so that's because it has to affect the concentration. And so let's say, you were just doing a reaction, reacting something with water in its liquid state. So if you add more water, this actually does not change your equilibrium. So it's a reactant, right? We're not changing the concentration, so this would have no effect. So this would be the same thing as adding in like a neat liquid reagent, like if you were using, acetone or phenol or whatever organic product. This could also refer to, so if we look at like carbon plus oxygen, so if you were trying to look at this equilibrium of making CO2, so your carbon is just a solid pile, right? So it doesn't matter how big your solid pile of carbon is, basically. It's still a solid pile, right? It has to react kind of surface-dependent reaction, so it's not changing the concentration either. So does that kind of make sense what it's referring to? And so going back to this equation that, again, we've seen in lab, the key here is they're all aqueous, right, in solution. So we weren't starting off with like solid iron metal here. We have aqueous iron 3+ in solution. And again, when you do this and stress it out, then you'll kind of see that better. All right, so that's at least a few of the base rules. And then let's kind of just go through this text, because the words, it's all just like kind of confusing, but let's just break down what it's saying. And again, we're saying, okay, we add reactants, and then, right, our rate of our forward reaction is not really affected. It's just the rate. So it initially increases the rate of the forward reaction, so no effect on the reverse reaction rate. So all we're saying is that if we add, and now let's take this example, so we have our system at equilibrium. If we add in more iron 3+, that's adding more reactant, so it shifts it away and makes more product, right? So if you added more iron, this would make it more yellow. And so blah, blah, blah. So our rate of our reverse reaction is not affected initially. So that would be, right, dissociation. So reforming our yellow. And so nothing really happens, but of course, like we see, right, our reactants get consumed. And so if we add more iron here, then obviously we're going to have less of this thiocyanate. So that's what it's saying here, right? So we have less of our non-added reactants. That makes sense. Obviously, they're going to be consumed to make products. And then K, right, not affected, so still the same equilibrium value, but might have different individual concentrations. But we're not going to get into the math in this class. And so then removing reactants, again, same thing. As long as it's not a solid or liquid, so it has to be something that's actually changing the concentration. And so if we removed a reactant here, and I forget how to remove reactants. I think for this situation, so if we want to remove reactants, so the key for this one is you have to find something that like complexes with one of these. So I believe in lab we add HCl, so this makes iron chloride, and then takes iron out of solution. And so now we're doing what the text says, right? So it says we're removing reactants. Okay, so what happens when we remove our reactants? And so, right, it initially decreases the rate of our forward reaction. So now we don't have, again, as many reactants to go forward. No initial effect on the reverse reaction. But then again, comparatively, just because the forward reaction is decreased, now we're going faster in reverse. And again, just kind of think about it without all the words. So we have our iron 3+. Let's say we added HCl so that it removed iron. So we're removing iron. And now that's going to cause our system to want to shift back and disassociate. So now if we have less iron, now this overall solution will turn more yellow as our iron thiocyanate just makes more free iron to compensate. Does that make sense? And so same sort of thing. So this one is a little different, the graphical representation. And so now this is showing if we add product. So right, again, system at equilibrium. Now we've artificially opened and disturbed it by adding product here. And so if we add more product, so now we basically have too much product, so that's going to increase our reverse direction. So AKA it's going to shift right to the reverse, so shift left, create more of our dimer. And then we see that, right? So we artificially spike that, and then now we have more N2O4 formation, and then our NO2 decreases, and then of course new equilibrium established. And so then we can think of kind of other ways that this is used, Le Chatelier's principle. And so another common type of reaction is called a condensation reaction. And so a condensation reaction usually forms water. So you have water, and then you're bringing kind of two products together. I'm trying to think of a good condensation reaction. kind of blanking right now for some reason on a good condensation reaction. Let's just ask the internet. Oh my gosh. I don't know if that was helpful. So usually it's some sort of alcohol and an amine coming together, which is what I was trying to go for, then I blanked. And so basically, blah, 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 they come together, make a new bond. So the rest of this doesn't matter. But the key point is that we form water. And so I wanted to just get into how we actually use Le Chatelier's principle. And so there's a ton of condensation reactions, which I know it's hard to tell since I couldn't think of any. And so this is commonly used in industry. And so let's see how they kind of drive this reaction forward. And so they use this apparatus called a Dean-Stark apparatus. So this is what it looks like. And so it's used for like refluxing or boiling a reaction. So this is the Dean-Stark shown kind of attached. So you have your flask here and it's boiling, and then your solvent can travel up here. We can get a more zoomed in picture. So right, you heat it up, your solvent travels up here, and then this is just a condenser, so it gets cooled back down. And then you have your solvent collecting in this little location over here. And so let's kind of explain what the Dean-Stark is doing, and then we'll look at Le Chatelier's principle. And so we have our reaction flask. So reaction here, so it's making water. And then we have our Dean-Stark. Sorry, drew that horribly. So Dean-Stark kind of going over here. And so the idea, and you have to plan this accordingly, so it doesn't work with every solvent, but most organic solvents are lighter than water. So water is going to sit on the bottom layer, and then you have your organic solvent on top that's less dense. And so what's happening is, right, you're removing the water from your reaction, so it's boiling, it's boiling, it's boiling, and then your solvent that you're doing the reaction in and the water collect on your Dean-Stark, and so that's removing your water. And so some of these get really fancy too, so notice this one has our little stopcock there at the bottom. And so that's actually if you release so much water that you need to kind of drain it a little and keep going essentially. So that's what that is for. And then we see, right, well this is how the reaction is driven forward, and especially because these condensation reactions, you know, some of them can be like several days, so that's one procedure that I'm familiar with. Like I had a condensation reaction that took 3 days of heating, and so to help drive that forward, right, you want to drive off the water. So Le Chatelier's principle, we're removing one of our products, right, so we remove our water, and then that causes the reaction to continue to shift forward and proceed in the forward direction, so going to the right and continuing to make products, so that helps your reaction go to completion. And so this sort of like basic Le Chatelier's principle would also be used in like industry too, to kind of control the reactions, right? So they're going to have kind of a streamlined process where your products are going away just to help keep moving that reaction forward. All right, any questions on Le Chatelier's principle? And once you do it in lab, that will probably help as well. Let's try to look at your lab and make sure people are okay with the lab. Let's see, which one? So how were your calculations going? So I felt a little better today because I know some people came in and worked on them. So did we figure out pre-lab 3, or do we still want to go over that today? So go over it. Okay, so let's go over it just so we're all on the same page. All right, so this is from our moles pre-lab. All right, so take just a minute or two to kind of look at it in case you haven't already, and then we'll go through it together. All right, so walk me through. What do we do? What are our steps here? Yeah, so at least just kind of start with what we're trying to figure out. So we have some unknown hydrate, calcium chloride, X. And so that's kind of the key, right? Is this lab is a good bridge between our stoichiometry and then trying to apply that, right? And so with some people, I've kind of been showing you our like proportion approach, but then being able to see that, how we can use proportions and how that relates to our mole-mole ratio is important. And so, right, the key is that we're making X equivalents of water as well. And so then what do we do with this information? What y'all do next? Yeah, so now find our difference. And so that's kind of the other thing is like we should pair together our pieces of information and what we need to know. And so this one, right, we have this 3.25 grams, but we can't really do anything with it, right? Because we don't have the true molecular weight. We just know there's an X, so we just kind of put that there. Then we have, okay, the mass of our samples, so that corresponds to calcium chloride. That's 2.45 grams. And then like you were saying, okay, well, let's find the difference. And that gives us, right, mass of water. So 3.25 minus 2.45. So what was the difference there? So 0.8 grams. And then what do we do with all this information? Yep, so we need to find, right, we need to get back to our mole-mole ratio. So we need to figure out, right, this mole ratio, because right now we have a 1 to X. But we can figure out moles of water, figure out moles of calcium chloride. So 0.8 grams. And then divided by the molecular weight. 1 mole of H2O. So how many moles of water did y'all get? So we have 0.8 divided by 18.02 or so. So like 0.044 moles of water. So 0.0444. And then do the same for calcium chloride, right? Because we have that number. We can find the molecular weight. So we have all those pieces. And then what's the molecular weight of calcium chloride? So 2.45 divided by that. So then about 0.0221 moles of calcium chloride. And so this looks good. And right, so if we were doing kind of the lab portion, and so the lab has what I call it ambiguous, and I accept different permutations of this answer, because it has this mole ratio expressed as a decimal, but it really doesn't say like what that means. And so it's fine if you put this ratio or like, you know, a similar sort of decimal ratio for your answer. So we can say we have 0.0021 moles of calcium chloride for every 0.0444 moles of H2O, right? Like that's fine. Or you could go ahead and convert it. And so the best way is to divide by the smallest number. So of course this goes to 1, and then we take our 0.044 divided by this number. Sorry. Try that one more time. There we go. And so we get a 2. And so you could also like write an answer that you have a 1 to 2.01 ratio of calcium chloride to H2O. So that would also be okay as a decimal answer, right? Because it's not clear what it means by decimal answer, but both of these are acceptable, or again, similar fashion for your moles. And then we can go ahead and round to our nearest whole number though, and we have calcium chloride with 2H2O. And then so kind of different notes to watch out for. So if you get like a 1 to 1.5 ratio, then you might want to multiply, times 2 or whatever to give you whole numbers so that it's a 2 to 3 ratio. And then if you get like a 1 to 1 1/3 or 2/3, those can be tricky. So those you want to try to multiply by a whole number to get rid of the decimal. So I think that's far to round sometimes. Like if you have 1.33, that could be a stretch. But then if we multiply, so now let's do this, 1.33 times 3. So now that gives us, 3 to 4. So that sort of thing. I don't know that we'll see weird numbers like that, but just kind of in case. And that's also where it's good to show your work so I can tell like how far you rounded. Because that can be a tricky judgment call over where to round and where to try to multiply by different numbers. All right, what else do we need to look at? I know we have a lot of stoichiometry issues still. Oh, sorry. Like I think I just picked a number, so I just try to remember the number because I've been doing this a long time. But yeah, like when you round, so the 10th place probably shouldn't see that much variability, but once you get out to the 100th, there will be rounding, so that's fine. So I'm just glancing at this homework, your chapter 6 homework. But in my opinion, it doesn't seem too difficult compared to maybe the stoichiometry issues that we're having. Is that a fair assessment? So should we do some stoichiometry practice for? All right, so let's try to do some more stoichiometry practice. All right, this is a good one. so let's try, I'm stealing some practice from Everett Community College. Go. So this is a good worksheet. So see if you can start with at least the first two problems. I can zoom in. So just go ahead, can you write that balanced equation for our sulfuric reaction, sulfuric acid with gallium hydroxide? And then if you feel okay about that, you can try to start number 2. So remember hydroxide is a polyatomic?
Yeah.
But yeah, hydrogen would be +1 from your,
Oh, wait. Oh, I didn't. Okay, sorry, never mind.
yes, oh, it's right over, so hydroxide's -1. And gallium's a little funny. What's gallium's oxidation state? Yeah, 3+, so I'll give people another minute to balance and write their equation. All right, somebody tell me at least the formulas. So what's sulfuric acid's formula? Yep, so H2SO4, so good. So remembering how to name those acids, so sulfuric with the sulfate, and then just pairing it with the appropriate amount of hydrogens. And then what'd you get for gallium hydroxide? Yeah, again.
Is it GA and then OH in parentheses 3?
Perfect. So gallium hydroxide looks good. And then it says it forms water. So we all know water is H2O, right? And then, oh, pop quiz. This is for your quiz. What's the formula for ammonia? What is it? NH3. Yeah, ammonia is NH3. So hint, that'll be on your quiz because there's a question kind of like this, except it's less hard. All right, so then we have water, and then what was gallium sulfate's formula? Ga2SO43, so that looks good. Right, so we said the gallium was 3 plus, sulfate -2, so cross multiply to balance. And then, of course, now we have to balance our equation. So did everyone get our coefficients? What do we get for this one? No guesses? I think we need more than one because we have 3 sulfates over here. So yeah, 3 is a good start. Let's see if that matches. So 3 sulfuric acid. And then, so now let's look at our galliums because we have 2 galliums though. So 2, so let's see how that works. And so now we need to balance our water, which sometimes I think of HOH to help me balance. Okay, we have 6 hydrogens coming from our sulfuric acid, and then 6 hydroxides coming from this, so I need a 6 there. Or I can tally it up, right, so 3 times 2 is 6 hydrogens, plus 2 times 3 is 6, so 6 plus 6 is 12, and then 6 times 2 is 12, so that works out. And then 3 times 2 is 6 oxygens, so 6 oxygens. Yeah. And then, so do we need more time for 2 still? So yeah, keep working on 2 now that we have our balanced equation. So how's this coming along? And we could also start with like key information that's helpful, just kind of like our knowns, so what would be good information that we need? Yeah, so let's go ahead and do that, right? So that's easy information. And so on a test, that's always a good thing, right? Write down your molecular weights of your compounds. That helps you. So now let's do, so we need our gallium sulfate molecular weight, potentially. We actually may not need it right now, but this could be helpful. Does anybody have gallium sulfate's molecular weight by any chance? Then we need sulfuric. So we definitely need our sulfuric acid molecular weight. 0.078. And then gallium hydroxide's molecular weight. Any takers? What did you get, Hannah? Yep. Oh, still calculating. Because you can just add up hydroxide, which is 17 times 3 plus gallium. I don't remember gallium's molecular weight there. So you said gallium was what, 69.723, and then let's just round 17 times 3. So about like 120.72 or 3. 120 point. So something like this, so could have a different number with rounding. And we can come back to gallium sulfate, though it does ask us for mass. But what type of problem is this? What's it asking for? Because it's asking, right, how much can be made with 145 grams of sulfuric acid and 320 grams of gallium hydroxide. So what kind of a problem is this? So we do need to get theoretical yield, but then how do we know what our theoretical yield is? So we do have to do that, but here, right, so it's a limiting reagent. So kind of what I was getting at is that we have to do our stoichiometry twice, right? Because we don't know which one is going to run out first, so we got to determine that. And so let's just go through that. So we have our sulfuric acid, and we're starting with 145. So I'm just starting with our 145 grams, then convert to moles, right? So dividing by our 98.078. 1 mole of our sulfuric acid. And so let's just punch in the number. I think that helps sometimes. All right, so now we're at 1.47 moles of sulfuric acid. So that's what we got out from our calculation. And so now we have to go back to our problem. And so it's asking for product here, so we might as well compare it to that. So it's a 3-to-1 ratio. So now we can set up our conversion. So for every 3 moles of sulfuric acid, we can only make 1 mole of our product. And it does ask for mass, but right now I'm not going to worry about that because we need to figure out, well, which one even runs out first. And so divided by 3. And so that means that I can make 0.493 moles of product. moles of our gallium-2 SO4 And so let's see if our other one is less or more. Oops. Ah. So now we have to repeat, sorry. It's the only downfall of trying to use a PDF is now I can't add more room. And so I'll squeeze this in there, so I'm just repeating, right? So now repeat with gallium. So I'm going to kind of make some space over here. So with our 320 grams of gallium hydroxide, let's try that again. So same process, right? So we're just converting 320 grams to moles. So dividing by our molecular weight. Could help to punch that in. So divided by 120.723. So then we have, right, this many moles, so 2.65 moles of gallium hydroxide. Moles. Now we go to our balanced equation. So right there in a 2-to-1 ratio. So for every 2 moles of gallium hydroxide, I make 1. And so now we can do our ratio. So 2 moles of gallium hydroxide make 1 of our gallium product. So then we can divide this by 2. And so now it's becoming evident, well, this is more, right? So now this is telling us this is 1.33 moles of product. And so this is telling us that our sulfuric acid is our limiting reagent. So less, right? So this is our limiting reagent. So we can only make this many moles of our gallium sulfate. So now we could figure out the mass. Did anybody get a molecular weight of gallium sulfate? You said 479? I have 427, but I didn't calculate it myself. Yeah, I think it's supposed to be 427. So let's, I already forgot what gallium's molecular weight was again. So 69.723, so times, so 2 of them. And so let's add our sulfates, that might be easier. So 32 plus, so 4 times 16 is 64, right? Double check my, and then times 3, so I'm multiplying all the sulfates. So that gives me 427. So I think that it's hopefully correct. That is so weird. Okay. This is a one-time. Wikipedia is like off. Look at this. I'm tripping over here. So it says 427, and then for some reason you click on the page, and it has a completely different mass.
Oh.
That is odd. Usually Wikipedia doesn't steer me wrong. We can also verify Sigma Aldrich, just so 427. All right, so I like our 427 number. So 427 point, and they have a different number, but I'll just round, so 0.45 or so.
So that, how did you get that
What I did, so I took the gallium, multiplied it times 2, and then I thought it was easier to get the sulfate weight, so I did 32, and then I just did 16 times 4 to give me 64, and then multiplied all that times 3. And then if I cheat and check online, it's pretty close, so. All right, let's finish this up so y'all can take your quiz. So then we can convert this to grams, right? So we can take our molecular weight, multiply it by our moles. So now that gives us grams of gallium sulfate. So 211 grams roughly of gallium sulfate. And so see if you can try this last one out. So now it's asking how much of the excess reagent will remain once the reaction is complete. And so think about the information that you have, right? You kind of already saw moles of this. Think about what you need to calculate, right? You're trying to find excess reagent, so how much was consumed might be a good starting point. So what did we come up for question 4? How do we determine excess reagent?
So you start off with the 0.493 limiting
Yeah, so this is, let's continue, right? So we found how many moles we could make. So now we have to think about, well, what are we comparing it to? So we already found out sulfuric was a limiting reagent, so don't care about that. So we need to just focus on our gallium hydroxide and our gallium sulfate. So basically we're trying to calculate, well, now that we know our sulfuric acid is going to be consumed first, how much of our gallium was consumed? So let's answer that. And so they're in a 1-to-2 ratio. And so now we can say, well, for every 1 mole of our product, we needed 2 of our gallium hydroxides. And so now we get how many moles of gallium hydroxide we needed. So 0.493 times 2. And so now we have 0.986 moles of gallium hydroxide consumed or needed. And so now we can convert this to mass, right? So we already have the information we need. So we already have it's 120. So now we can just take this, so times our molecular weight of gallium hydroxide. And so that gives us about 119 grams consumed. And so let me just write that out. So 0.986 moles of gallium hydroxide. So we just wanted that in grams. So times 120 grams per mole. And so that's 119 grams of gallium hydroxide, again, consumed. And so then the last little bit, right, we could just now take the 320 that we started with minus the 119 to give us how much was left over. So now about 201 grams or so were left over. Any other last thoughts or questions on that one? Oh, that was just from subtracting. So we had said we initially had 320, and then I subtracted the 119 that we got, so how much was actually used, so that gives us the 201. All right, I'm going to hand out your quiz, but then if you want to go take a break, you know, go for it. I know some people want to get started.
She texted me this morning and said she was going to Blitz